So read the first problem, first of all, to yourself. I need to get one more thing set up here. And then go ahead and solve it. This is a pretty weird problem. I'll do it in just a second here. I need to get one other little thing set up on here. Okay, so what this is basically saying, related rates problems, these are applications of derivatives primarily. And what you typically have, this is kind of the structure of the problem. Generally, what you'll have is, usually I give one rate, and then you find another rate. So if you're asked to find a rate, then you're talking about some sort of a derivative like that. So to begin with then, what I want to go ahead and look at is, let's read the problem and kind of get everything put together. What I try to do on related rates is take you through this process. Okay, you follow these steps because these are all the things you're supposed to think about. So first of all, what this problem is saying is this. You got Bigfoot here, and you got the sun, and then Bigfoot is moving. That's the shadow, okay, based on the angle of the sun. And then what you're doing is, it says that that's fixed at 12, I think 12, what did that say, 12 feet, okay? Bigfoot's 8 foot tall, and what's happening is that rate of that shadow is changing in some value like that. So based on this information, okay, you always have to read the problem. You have to very carefully think about what you've been given. And you have to draw a picture. Get a picture down first of all. That's a real key. And so the idea is, this thing right here means something. This is real important. It says, walking towards the street light at a rate of 2 feet per second. That's a derivative. Okay, so that's the first thing you got to do. Remember I said I give you one rate. That's a derivative. So we're going to kind of begin to write down what we have. Okay, then it says the light is 12 feet high. What rate is the length of Bigfoot's shadow if he's 6 feet from the base? So that's going to be 12. That's going to be 6 like that. So what we do is we need to kind of see how all the variables relate. That's the first step, is after you got a picture, you've read the problem, try to figure out mathematically what's the relationship between all these variables. So what let's do on this has to do with triangles. So let's draw a kind of a triangle somewhere. You can just kind of write this on here. We got two triangles. The way I look at this is we have two right triangles. Okay, we've got this one right here, and I'm going to just sort of highlight this triangle right there. Okay, and that triangle has a base of y, and it has a height of 8. That's what you know about that triangle, right? Okay, then we have a bigger triangle. We have the big triangle. Okay, and let's see what we have there. So the big triangle would be, of course, the whole entire thing. And let's kind of label what we know there. In that big triangle, what's the base?
X plus y.
X plus y, right. Okay, so you just add those two things up. Okay, the height is 12. So we're going to look at a mathematical relationship between those variables. And what this is these are similar triangles. This is a geometry thing students a lot of times don't do much with. So they're similar triangles. And if you ever did any geometry in high school, you may have learned this, that if two angles are the same, then the triangles are similar. We call that angle-angle similarity. Did you ever learn about that? Maybe, maybe not. And did you ever deal with similar triangles? Okay, the thing that you learn about similar triangles is their sides are proportional. For instance, if you had like 3 and 6, and if you knew that this was 6, that would be 12. 3 times 2 is 6, 6 times 2 is 12. That's what similar triangles are. It just means the sides are proportional. Yeah?
I was wondering if this is in relation to the SSA and SSS triangles?
Yes, well, yeah, kind of. But when you're talking about similarity, generally two triangles are similar if you know that there's two angles that are the same. And we do. They both have right angles, and then that base angle is the same. We know that for a fact. Okay, so what we do is they're proportional. So what we can do is you can write these proportions in all kinds of ways. So, for instance, if you had this same situation, say that that was 3 and 6, and then let's say that you multiplied everything by 3. So that became 9, and then 6 times 3 became 18. Well, notice on here that if you do 6 over 3, like that, that's the same as 18 over 9. So that's a proportion, right? You can tell they're the same. So you can write this proportion in lots of different ways. I've decided I'm just going to do this way. I'm going to have you write 8 over y is equal to 12 over y plus x. And then we're going to solve that equation for y, because ultimately that's what we're interested in, is that rate that the shadow is changing. And that shadow is represented by y. Okay? Does that make sense? Now, those are similar triangles, and that's a big deal on these related rates problems, some of them. So let's write that down, and let's go ahead and solve this equation for y then. Okay, we're going to cross multiply. The simplest way to do that is just cross multiply. So I'm going to go ahead and have you do that. So that would be 12 times y is equal to 8 times y plus x, like that. Let's get that solved for y. So it's going to be 12y equals 8y plus 8x. Okay, then I can subtract 8y from both sides. Okay, like that. Try to get it down as far and simplified as we can. So that looks like that's 4y equals 8x. Then I can divide by 4. So I get y equals 2x. So that's a real big deal. We got the relationship between the variables. Okay? Yes?
Don't you already know that x is 6?
What's that?
X is 6. Isn't that what we already covered?
Yeah, we're to there. We'll get there in a minute. Yeah, we're not quite there yet. What we need to do right now is we're going to know that that x is 6, because that's given in the problem. We want to go ahead and start the equation, because we have to do something with that equation before we get there.
So you wouldn't plug in?
No, you're going to do that later, though.
Okay?
Yeah. And you'll kind of see why, because we have to actually differentiate both sides of this equation to get the rate. Okay? And if we did that right now, then you would end up having that rate would be 0. If you differentiate it, see, if you plugged in x is 6, you would get 12, right? If you did the derivative, you would get 0. Okay, we're going to get a general formula for that derivative is what we're going to do, okay? Okay, now, next thing is, let's kind of figure out what do we know. Well, one thing we know, and you just said that, is x is equal to 6. Okay, that was given. That's just the distance that Bigfoot is from the pole. Okay, we know that's 6. That was given, okay? The other thing is this thing right here, and this is a real key. Remember I said that I always give you a rate. So that says that you're walking at a rate of 2 feet per second. And what that is now is that's the rate that he's walking. So then what that's going to be represented by is that's going to be, and you have to write this the right way, that's dx, okay? That's the rate that x is changing at a particular time. These things are always going to have time in it. So it's dx over dt. And then that's going to be equal to, since he's going towards that, we're going to represent that as negative 2 feet per second, because that's what that says. All right? And the idea with this is you want the signs to match up a certain way. The reason I'm doing that is because that distance is decreasing. So as he goes towards that light, it's getting smaller. So we're going to use that as a negative direction. So that's what we're given. Now, what I've done is I've done the hardest part of the problem for students. Typically, finding the relation, it can be challenging, and then just listing correctly what you know sometimes students don't do so well on. So I'm ready basically now to put the whole thing together and get a solution to this. So what you're doing with this is the question says, at what rate is the length of Bigfoot's shadow changing? Well, what variable is Bigfoot's shadow? Y. That's the whole key, is you got to know what the variables represent. Y is the shadow. X is the distance from that. And see, they gave you the distance, the rate of change towards the pole is negative 2 feet per second. That's why that's dx over dt. Does that make any sense? Okay. Now, here's what we're going to do. Write down your relationship. So we got y equals 2x. and then we're going to differentiate this. And we're going to differentiate it with respect to time to do that. And then the last thing I forgot to do before we do this is what we want to find. What you want to find is a rate. You want to find dy over dt. Okay, that's the idea. Because that's what it says. What is the rate of Bigfoot's shadow? And that's represented by y. Okay, you guys following what I'm doing so far? There's a lot of little things going on, and you got to be very clear about what you're given and what you're trying to find. To me, that's the whole key to solving any word problem anyway. So now we're going to multiply. We're going to take a derivative with respect to t of both sides. The reason we're doing that is because we're trying to find dy over dt. That's our goal. Okay, and we got it. Notice when we do this, we have dy over dt on that. Okay. So that's what that's going to be, and then this right here is going to be, when you do this, when you do the derivative of 2x, that's just going to be 2, and then the variables don't match, so that's going to be times dx over dt like that. Okay, so that's what you end up having. That's your derivative. Okay, so that's a real simple derivative, and again, does everybody understand why I got the dx dt there? Variables don't match. Okay, then that's just dy over dt. Okay, so now what you're ready to do is you're ready to plug in the particular information. All right, so what we end up having on this is there's only one thing that we got to plug in, and that's that. Do you know what dx over dt is? Yeah, that was something you were given, so you plug it in. So what you would have is you would have dy over dt is equal to 2 times, and then that would be negative 2 feet per second, like that. So then the solution to that problem is you would have dy over dt, that's the rate that Bigfoot's shadow is changing, is negative 4 feet per second. That's what that is. That's what that represents. So then what this says is you want to write the answer a certain way. Now here's where the 6 comes into play. Is you say when Bigfoot is 6 feet from the base of the light, because see that rate changes. That's the rate at that particular point in time. So that rate is negative 4 feet per second. And it's negative because it's decreasing. That's the reason for that. Okay. Now it's pretty abstract. That kind of gives you the idea of some sort of a rate of change like that. Okay. So that shadow is going to be changing like this. Basically, it's represented by 2dx. Okay, so it's always just 2 times whatever the rate is, depending on where Bigfoot is. That's the idea. Okay, is there any questions about that? Okay, now one of the reasons I don't test on this on test 2 because it takes students time to learn this. Okay, you have to do homework and practice, and you got to wrap your head around this a little bit. Yeah.
Finding dy of dt and not finding the rate of change of the shadow, or just finding the rate of change of in between the light?
No, we are finding the rate of change of the shadow. That's what y represents. Okay?
Oh, okay, I see.
But the thing is, what x is a specific distance. If I change that, basically what you're going to find on this is no matter where Bigfoot is, it's still going to be the same rate. The shadow is still changing at the same rate, and that's just because of the fact that it's going on in a triangle, so it's kind of got a constant rate of change. So that's the idea. So the thing is, when you do these problems, you want to make sure you're real clear on what every variable represents. That's a real key. Y is the shadow, x is where Bigfoot is from the base of the pole. That's the idea. Okay? Is that fairly good for a start? Okay, all right, let's move on. The next one's a great problem. I love this problem. You'll like this problem. So, with this one, let's go ahead and see if we can put this one together. Okay, now what they have on this one is, so here's what we have. We got some people who are very thirsty. So this is the wine barrel problem. So the idea with this is you have sort of a cone-shaped container that's got a bunch of wine in it, okay? And these people are, getting sips of wine. So the idea is there's several things that are going on there, okay? It's 12 foot deep. I like to kind of, highlight what I have. It's 12 foot deep. That's represented right there in the diagram I gave you. That 12's in there. Okay, so we got that. Okay, then the other thing it has is, well, let's see, it's got a 6-foot radius at the top. So that's also represented right there as 6. So those things are given to us like that then. Okay, then it's saying the wine is disappearing at a rate. Remember I told you I always give you a rate, right? That's the rate I've given you. So the wine is disappearing at a rate of 6 cubic feet per hour. Okay, we're going to talk a little bit about how we formalize that because that's a piece of information we know. Then the question becomes, what rate is the depth of the tank going down when the depth is 4 feet? Okay, so basically what's going on this is, let's try to think about this a little bit. Let's think about what you would know would happen on this. Okay, so basically if you open that up, it's going to drain. You obviously know that, all right? But is that rate going to be always the same? Is that rate going to change? That's the question. To me, what would happen is if you opened up the plug, I mean, does it start draining faster at the beginning or faster at the end or what? That's what we're going to find out, okay? You've got to think about how that works, okay? So we want to go ahead and see what kind of relationship we have in the variables, and you have to know something about the volume of a cone to do this. So if you don't know that, you'd have to look that up. So what I'm going to do is draw a picture, have you draw a little picture on this. This is the way I look at this, is kind of like this, is at the side, let's just draw a triangle. This will help you, I think, kind of see this. So what you have is the radius is 6. Okay, that's a 6-foot radius. I think it said the whole entire height was 12, like that. Okay, and that radius is going to change. So see what's going to happen. The radius starts 6, but that radius is going to get smaller. Agreed? As it drains, the radius is going to get smaller. The other thing that's going to change is that we call h. So those are kind of the two key variables in this problem. The radius is going to get smaller, and the height is getting smaller, and both of them are going to 0. Agreed? Okay, I'm going to do like that. So we're going to see if we can come up with an equation. Well, we're dealing with volume here. So the formula for the volume of a cube, you'd have to look that up as 1/3 pi r squared h. If you need to write that a note down to that, that's the volume of a cone. Okay, so that's what that is. So if you didn't know that, you'd have to have that piece of information then. Okay, so what we're going to do on this then is we're going to differentiate this. There's a few things on here that we also know here. We got to get this down to one variable, and that's another thing that's real key when you do these problems, is you got two variables there. You have an r and you have an h, okay? So when you're looking at this problem, we also have similar triangles going on here again. So what I'm going to do on this is we're going to do a similar triangle thing. So what we have is that triangle there, and then we have the big triangle. They are similar triangles because they're both right triangles. They both share two angles, okay? They both have a right angle, and then that angle right there is the same, okay? So let's put a relationship together just like we did the last problem. Let's go 6 over 12 for the big, and then what would that be in the small triangle? What's that going to be equal to? 6 over 12, what does that relate to? R over h, good, right. 6 is the radius, so the radius goes there. 12 is the height, that goes there. So what I'm going to do is I'm going to solve this for r. Now I'm going to talk about why I'm going to solve it for r. The reason I'm going to do that is because look at what you're trying to find. It says, what is the rate of the depth? Okay, the depth is represented by which variable? H. H is the depth. I want H to be a variable in this equation because I got to differentiate it. So what I'm going to do is I'm going to solve this for R and then replace that R with something because I want H to be my main variable. Everybody got that? Because it says what's the rate of the depth. Okay, that's the key. So cross multiply this, or you can just do this. You can just multiply both sides by H. So you're going to get R is equal to, then that reduces to 1/2 h like that, okay? So what you're going to do now is this thing is going to plug in here. So that thing, just plug it in, and then we're going to have what we need to differentiate. Okay? So since it's a volume of a cube, you had to pull out that formula, and then you've got to set it up with one variable. And that's real important. When you differentiate, you got to get this down to two variables. V is the volume, and then just one other variable. So we're going to have V equals 1/3 pi times 1/2 h squared times h. Okay, then we need to go ahead and solve that, get that down as simple as we possibly can. So that's going to be 1/3 pi. If you square 1/2, you're going to get 1/4. Then you have h squared times h. So if you put that together, here's what you have. You have 1/12, and then you have pi, and then h to the second times h to the first is h to the third. Okay, so that's the main connection between the variables. That's what we have. That's what we're going to end up differentiating. Okay, so what did I do on that? I have a volume formula, and I got the reason for this triangle step over here is because I have to have only two variables. Everybody with me on that? Okay, and because it says the rate of the depth, that's why I want h in my equation. Okay, you must pay attention to that. That's real key. Now we're going to go through and we're going to look at everything that we were given. Okay, so the first thing that we were basically given on this is it says this, they have this rate. It's disappearing. Disappearing means that you're going to use a negative number, right? Okay, because it's getting smaller. And what that is it says the wine is disappearing. To me, that implies that the volume is changing, right? So what we're going to say is dV over dt. That's given as -6 cubic feet. So that's cubic feet. That's what volume is in cubic units per hour. So that's a piece that we're given. The other thing that we have is it says what is the rate of the depth of the wine when the depth is 4 feet. Okay, so in this diagram, that's what h is. So we also know that h is 4 feet. Okay, like that. All right, those are the two key things that we're given that are going to allow us to get the problem put together. So I've done the hardest part of the problem. The rest of it is mechanics of calculus. Okay, is there any question that you have about the relationship or anything? Okay, now what we're going to do is the question is what's the rate of the depth of the wine? So what that means that what we're trying to find is we're trying to find dH over dt, right? Because that's depth. Okay, pay attention to what everything means. So that means you're going to go ahead and write down this formula, 1/12 pi h cubed. And what we're going to do is we're going to do the derivative with respect to t of both sides. Okay, we're going to find dH over dt. So we're going to do like this, ddt of v equals ddt of 1/12 pi h to the third, like this. So now it's just calculus skills and differentiating. Okay, left side. How are you going to write the left side? dv over dt. Do you know dv over dt? Yeah, I gave it to us, so later in the problem we'll have to use that, right? Okay. Now what's this derivative? Well, you got a constant. You got 1/12. Pi's a constant. Pull it out. And then you're doing the derivative of h to the third. So how are you going to write that? 3h squared times dH over dt. See? Variables don't match. Implicit differentiation, you got to write dH over dt. And after all, what are we trying to find? We're trying to find dH over dt. So it's got to be in your equation. It has to, right? Okay. So now what we need to do is we can now just sort of plug everything in. Now I'm going to go ahead and solve this now for dH over dt. So I'm going to work on that a little bit before I plug everything in. So I'm going to have dV over dt. Notice a couple of things on this. 3 over 12 is a fourth. Okay, so I'm going to end up really having, I'm going to write this just as pi h to the second over 4 times dH over dt. And then we're going to solve this equation for dH over dt. Simplest way to accomplish that is to multiply by the reciprocal of that number. So we have 4 over pi h squared 4 over pi h squared like that. Everything will cancel. Now we've got what we're looking for is a formula for the rate of the depth of the wine with respect to time. So that's going to be 4 over pi h squared dv over dt. Okay, like that. All right. All right, so what we'll have then is now we're ready to plug in what we know. All right, so is everybody okay with the derivative? Does that look okay to everybody? Okay. Now we plug stuff in, and then we're going to get the official answer to the problem. So when we do dh over dt now, okay, what we have is you have 4 over pi h squared. You know what h is. H is 4 feet. Now I'm going to put the units in. Like if you guys get into physics here and start taking physics classes, it's real important to understand how units work. So I'm going to put in 4 feet and square it because I want to show you how the units work out again. And then what is dv over dt? That was -6, right? Okay, so you plug that in. So what you're going to have now is dv over dt is the same thing as -6 cubic feet per hour, like that. And then we just got to work out the math and the arithmetic on that. We're going to use a calculator mostly on this to see what we get. Okay, so let's write a couple more steps, and then we'll use our calculator. So looks like I'm going to have -24 cubic feet in the numerator. Then I've got 16 pi, 4 to the second, and then pi, square feet. And then I still got per hour. I'm going to put the hour there in the bottom like that, just to show you how units work. Okay? All right, well, what I'm going to do now is I'm just going to get the calculator out. I don't even need to reduce the fraction or anything, so I'm just going to go 24. It's a negative answer, so it's 24 divided by 16 pi. Notice that I'm putting parentheses around the denominator. You want to be careful about stuff like that. So then that would give you approximately that rate. And I'll round that off to like 2 decimals, so that's about -0.48. Now, what are your units? There you go, feet per hour, and I want that to make sense to you. Okay, that's feet because the third power, second power per hour. Okay, depth. What is the unit for depth? Isn't that just feet? Okay, it's not area or volume, it's just depth. So see, the units are working out in a logical way. So what that is saying is, when you put this all together, is when the wine gets down to a depth of 4, it's changing at that rate like that. Okay? So when we write the answer to the problem, it goes like this. We would say basically, at a depth of 4 feet, okay, we would just say the volume of the depth, not the, because we found, remember we found dh over dt, not the volume, so it's the height, but the depth is changing. So we would say the depth is changing at a rate of -0.48 feet per hour, like that. So that's the idea. Okay. And one thing that would happen on this is if you were to put this, you could actually graph this derivative and you could get a sense of how that's changing. Okay. So let's go ahead and, do you guys have any questions about how I put that together? First of all, that's my thing. You guys follow what I'm doing? Sometimes students just don't get this stuff very good at the beginning. So what I try to do on teach related rates is just go through that process and follow those steps exactly. And even when I test over this, I generally have you go through those 6 steps. I even write those 6 steps on there to kind of guide you through that, okay, because it's a thought process that you have to do then. Okay, and the question kind of that I had in the beginning was, in this problem that we just did, was, how is the rate changing? Well, I did a couple of graphs on here, and I just want to show you these 2 graphs. So if you take the, let's see, the volume, which is this, that represents the volume of that particular cone. And I graphed that on my calculator, 1/12 pi h cubed, I used x. So the depth started at 12. So when the depth is 12, the volume is almost like 400. That's what my graphing calculator is showing. When the depth is like 4 feet, which was out here somewhere, then we had a different volume. So first of all, what's happening on this is you always have a positive rate of change on that, and you're kind of going backwards with this, kind of like this. So the tangent line is the steepest right there, right? And then what happens is as that gets smaller, the tangent line gets smaller, right? So the question I had was, when it drains, does it drain fastest at the beginning or at the end? What do you think? At the beginning, if you think about this, right? Okay. Because right there, that's when the slope of the tangent line is the biggest. Okay, right at the beginning. And then when you get down to where it's almost totally drained out, then what's happening? Then the rate's almost 0, right? Okay, that's the way it happens. Okay, it kind of seems like it might be opposite of that, but it isn't. And then if you do the derivative of this, the derivative of that is pi h squared over 4. That's what the graph of the derivative looks like. It almost looks like the same graph. But the idea is you have the biggest value, the biggest rate of change is there, and then like when we were at 4, you had a real tiny rate of change. It was only like 0.5, okay? So that's kind of the way that works out. That's kind of a good way to look at these problems too, is graphically, okay? Okay, so let's do this last problem here, and I just like to kind of give you 3 examples just for a little bit of variety of the situations we have here. Okay, so what this problem is saying is you basically have this situation. Now you have an observer down here, and let's see if it's read through this. It says you have a UFO. It's at a constant altitude of, I think that was 3 miles. So in my diagram right here, this is supposed to be 3 miles right there, like that's on your handout. Okay, and then what it's saying is the UFO is moving away from the observer. The observer is right here, and a person's taking a picture on their camera like that. So the idea with this is, let's kind of see what it says they have. So it says that we have the instant the UFO had already flown horizontally 4 meters or 4 miles past the point directly above them. Okay, so it's going to be flying in some direction that way, so that's going to be the 4. They say that the radar gun showed that at the instant the photograph was taken, the distance was growing at a speed of 384. So what is that 384? What did I say I was always going to give you? A rate. A rate, that's a derivative. Okay, and it says speed, rate, so 384 miles per hour. So that's what that is. So what you're going to do is you're going to determine the speed, which is a rate of change that the UFO was traveling. Okay, so the first thing that you got to do on this is you've got to kind of look at what the relationship is on this one. And really, you got a right triangle on this one. So it's a pretty straightforward relationship. Let's just draw a right triangle. And what we have is we have 3, we have x, and we have c. Okay, but what it says on here is it says the UFO had already flown horizontally 4 meters past the point directly above them. So I'm going to write this as 4 miles because I'm interested in that particular point in time. So that's 3 miles, and then that's 4 miles like that. And remember, we're coming up with a mathematical expression that we can differentiate. That's the ultimate goal on these problems, is getting an equation that you can differentiate, okay, to find that rate of change. So basically, this relates this way. This is Pythagorean Theorem. So you know that c squared, that's the hypotenuse, is equal to 3 squared plus 4 squared. So that's going to be c squared is equal to 9 plus 16. And you may already know that's a 3, 4, 5 right triangle. Then you square root both sides. So you're going to get c is equal to 5. Okay, so that's what that ends up being, is that then. So what we're going to end up doing with this then is that's going to end up being that distance right there. Now what we need to go through and do with this is look at the more general equation. like this, which is going to go like this. We're going to leave x as a variable, and that's going to be 3, and then I'm going to write that as c. So I'm going to set that up. I need to know what c is ultimately. But in this problem, I'm going to leave x alone, because what we're doing is we're interested in ultimately is the speed of the UFO, and that's going to have something to do with x. Okay, so what we want to have now is if you do the Pythagorean theorem, you're going to get c squared is equal to x squared plus 3 squared. So that will be c squared is equal to x squared plus 9. So that is our kind of our key thing right there, is that's the key equation that we have. All right, that's what we're going to work with the derivative on, but we do need to know something about that fact that we can tell that at this point in time, when that is 4 miles away horizontally, then that's also 5 miles like that. Now that's Pythagorean theorem. So some of these problems will just strictly have to do with Pythagorean theorem. Okay? All right, so that shouldn't be too bad. Now we need to write down kind of what we're given. Okay, so first of all, it said that this is your rate right here. You got to identify what rate this represents. Okay, so if you read this, this says the distance between the photographer and the UFO. Which variable represents the distance between the photographer and the UFO? C. Good. So that means that that rate is dc over dt, right? Okay. You got to read these problems super carefully and know what everything represents. So that rate right there is then going to be something that we know. So that's going to be 384 miles per hour. Now the reason I'm going to use that as a positive is because that, this is, the UFO is going away from this person, really. Okay, so it's moving away, so we have that. The other piece of information we have is x. If you read the problem, it says the UFO had already flown horizontally, that's a key. The horizontal distance is x, right? 4 miles from a point directly above, so x is 4 miles. That's another thing you're given, right? Okay, so we have that. All right, so we have those two things. We also have c is equal to 5 miles. That's the reason I kind of did that to start with, is just find that. So I've got that. Those are things that we know. Now what we're trying to find is this. The key thing is it says determine the speed at which the UFO was traveling. Okay, so what is a speed? A speed is a distance over a time, right? What is the distance that the UFO is traveling, not from the observer, but what's its distance?
4 miles.
Okay. What is its, I should say it this, what variable represents the distance that the UFO is traveling? X, good. Okay. So that means that what you have here is you're trying to find dx over dt. Okay. So you got to know what the variables are. The x is the distance of the UFO. C is the distance the UFO is from the photographer. So they have different speeds going on. There are different rates going on. Okay. So now we've got everything we need to know. Like I said, that's the hardest part of the problem. You got to find two things. You got to know the equation, and you got to know ultimately what you're differentiating. So we're going to find what dx dt is, and we're going to use these given pieces of information. Okay, everybody with me so far? Okay. All right, so let's write down our general equation, which is c squared equals x squared plus 9. And we're going to differentiate that with respect to t. You always do these with respect to t. We're always thinking about time as a variable. So we're going to differentiate c squared. We're going to differentiate x squared plus 9. And then we'll do that implicitly and then kind of see what we get. Okay? Well, okay, let's be careful when we do this now. So what's the derivative of c squared going to be? How are you going to write that? 2c dc dt, right? Okay, variables don't match. That's important. And see, you know dc dt. You know it's a part of the problem. Okay, so you have, 2c times dc dt. Okay, then the right side, you have 2x, then what do you have? dx dt. Good. And then you have derivative of 9 is 0. Right there. Okay, so you got that. Now see, notice that you have everything in here. We know c. Okay, we got that. we know DC. That's in there. And we know X. See how we know everything? The only thing we don't know is dx over dt. Okay, that's the way you'll kind of know you're on the right track if it works out this way. So now what we're going to have is you can actually just divide both sides on this problem by 2x to isolate this then, like that. So if I do that, the 2's will cross out. That will leave you with c over x times dc over dt. And then that's going to be equal to dx over dt. Now we're ready to plug everything in, and then we're going to have our answer and kind of think about our answer then. Okay, so we just plug everything in now, and I'm going to use the units again. I want you to always pay attention to your units, because if they don't match up the way you expect, then something's going seriously wrong. What are the units for a velocity or a speed? Miles per hour, right? Okay, we better end up with miles per hour or we're messing up, okay? So when you start studying physics, pay attention to those units. It's real important. So we'd have C is what, 5 miles. Okay, so we got that. Okay, X is 4 miles, so the miles are going to cancel out, okay, at least in that piece right there. And then dC over dt is 384 miles per hour, like that. So yeah, okay, we get the units we're expecting to get, so that's a good sign. And then you can just do that on your calculator. So I think I've already got that. You can check my calculation. I think this is 480 miles per hour. Did somebody check that?
Yeah.
Okay, good. So that's it. Okay. So see, what you're doing on this is you can kind of indirectly figure out what that rate of the UFO is. Okay. If you knew what one rate is and you knew what those quantities were, then you could figure that out. Okay. So that's the idea. So when you're writing the answer, what you're really doing on this, you're really saying when the UFO, because I always want you to write your answer a certain way, because I want you to, and the purpose of that is to try to show me that you understand what you're finding. It's not just a number. What does that number mean? So it's really when the UFO is 4 miles horizontally from the observer, and just abbreviate some of this, then the UFO is traveling at a rate of, and that's what we found, a rate of 480 miles per hour, like that. So you can kind of state it something like that. But the key thing was the UFO was 4 miles horizontally, or you could even say 5 miles from the observer if you wanted to, like that, directly from the observer, then that's what the rate is. So that's it. Okay? Okay. Does that make sense? Okay. These things are kind of hard to teach too, but one of the things I've tried to do is take you through this thought process, and then that'll help you a little bit, because you guys are going to go on to engineering and calculus and physics, and I know a lot of you are going to be doing that. This is the kind of stuff you get into all the time. Okay? This becomes a super important